Okay, so let's continue with the parametric representations of a curve in the plane. Okay, so let's share the screen. Okay, can you see already the notes?
Yes, sir.
All right. Okay. We have a parametric representation curve. Curve, say curve gamma. Okay. And the representation, parametric representations. Meaning that you're adding a parameter t. T as time. I mean, you're considering a curve as a path of a particle. Particles moving. Okay. So when you think curve as a path moving, then it is basically a motion. And as a motions, you have mechanics. You have positions, you have velocity, you have accelerations. Okay, you have mechanics. So you have first say if the parametric is the positions, then the derivative is velocity, and the second derivative is accelerations. And as a path, you have meaning you have directions. Okay. So suppose you have a unit circle. Unit circle is just a curve, right? So without directions, but with parameter, then you see the circle is a path of a particle moving in a circle. So it has directions, it has speed. Okay, so that's the basic idea of the adding a parameter. So the most basic thing is that let me just okay. So this curve gamma uh, describe the x parameter as a function, say ft, and y as a function t g. Okay, with t in some interval between a and b. So this is an example is this, for example. So the curve gamma is described as say square with t, say from 1 to, okay. Let's compare this one. T, okay. And another is and y is t to the 6. Same t between 0 and 1. Okay, so let's see. Now the idea is that you have to find somehow relation between x and y. Okay, always we eliminate, because this is the important thing, is that eliminate t somehow. And so find relation between x, y. Okay, so you see in this case, you see, this is a square, this is power 4. So power 4 is the square of the t square. Okay, so you see from here, y equals x square. Okay, y equals x square, and t from 0 to 1. Okay, so the graph looks like this one. Well, you know that the y equals x squared, this is parabola, but then you start from 0 here. So you start from here, and you end up with a t equals 1. So this is 1, 1. And in between, you're going these directions. So actually the curve is this one. So this is a part of the parabola. Okay. Okay. And here you see, this is also, if you solve this one, you see this is y also x squared. So this is also a parabola. Going from the origin to 1, 1. This is 1, 1. Okay, and going this direction. Right, so this is part of parabola also. Okay, and you have also the third one is, hey, that's the same because, oh, also and this gives you also the same picture, starting from the origin to the point 1, 1 in this direction. Okay, so you see this, all three, the shape, the curve is all the same. Okay, now what's the difference between them? Well, the direction also the same. The starting point same, the end points the same. So almost everything the same, but you will have some difference in later if you take the velocity, for example. Here the velocity is just 2t and t 3t cube. At points here, the velocity is different from different here. Case 1, case 2, case 3, different in velocity. Okay. So the idea here is shape has various parametric representations. Okay. Okay, might be different in may differ in velocity or direction. Okay, let's see. Another example is that, well, one that you know, uh, suppose you have, you know, this is cosine, is this sine, t0 pi. So you have only this part here, that brackets. Okay, but also you can have this, for example, and then y is square root of, say this is 1 as t squared. Okay, and t from 0 to the, let's see what you have here. Starting from 1, in this case, 1 to 0. It doesn't match instead you get the semicircle, but then the starting point is different because here you start from 0, 1 to, let's see, 1, 0. I want to have, let's see, if you have this one, then you start with t equals 0, so 0, 1. But at t equals 1, you have 1, 0. Okay, so it doesn't match. Let's see. So from t going only this direction. So to match this problem, you gotta have let's see, maybe this one. Get the same as 4 in terms of directions. Okay, maybe we should use this one. Because we start with 1, right? So it should be 1 minus t equals 0, 1, and then here, so 1 minus t this. Okay. All right. So what you have here, 1 minus t. This one is what you have here. 1 minus 1, that's if t equals 0, then this is 0. That's not good. That's not good. Better one, it should be like this. But here, not from, but t from -1 to 1. Okay. If t equals -1, so you really have from here going there. Right? The only difference is that you're going the opposite direction of what you have in here. Okay. So the question is how to reverse the direction. So we'll do that later on. Okay. So at least we match the curve. So it's upper semicircle, but different the different directions. Opposite directions. Number 4. Okay. So the idea is that you can always, well, if we have a parametric representations, it is not unique. So the idea here is the, yeah, okay. And one more thing. Suppose you have we have a graph of functions. Y equals f of x. Okay, so x between say a and b. Okay, then we can make parametric representations. X is t, y is f of t. Okay, so then this gives you a t nodes between a and b. Okay, so this is give you the parametric representation of these functions. Okay, so if you have a functions graph, then you can change into parametric form. Okay, but not the other way around. May not be a functions. Okay, so that's the easy part. Okay, I guess that's from parametric form. Okay, and once you have a parametric form, it's easy to make a curve on space. In space now, not in uh, the plane on the plane anymore. Okay, can be extended to curve in space. Okay, so for example, this one, curve gamma is, say this is cosine t. Again, this is our favorite example, sine t. But then you have z. Okay, we say this is t square. So t from 1 to 2 pi. Okay, so what is this? Okay, so let's draw the the axis. Now this is the convergence. The one facing us is the x-axis going towards us. Okay, so it's in form of uh, forward, backward. Y is going left and right. Z is going up and down. Okay, so that's the idea. So I would say this is y plus z plus. Okay. All right. So we have here, if you restrict to in the plane, xy plane, so you see what's the relation between x and y here? Well, again, this is cosine and sine, so you have, okay, so this is a circle, especially because you start from initial point, is this one. So this is the initial point. And points also here, because you are going one full circle. So you have here. Okay. But then you have also z directions. Okay. So you're not only restricted to xy plane, but going, see the endpoints now, you have a height here, 2 pi and then square. Okay. So in the end, you're going this way. Well, you're like going on a tube. Okay. So you're going this way. Here. Okay. So it's like a spiral thing, especially if you say not t is not 2 pi, but say 6 pi. So it's like a this example spiral. Okay. So now later on we will use this to describe how to write an equation for lines on in the on space, on three space. Okay. Hey, questions? All right, so let's move to some more things about factors. Let's move to this. Let's see. Okay, let's do some before that. Yeah, forgot to do this one. Okay, let's back to here. Let's do some calculus on this curve. Okay, so suppose you have a curve, um, parametric curve, say gamma, which is x of t. All right, so and y is a g e between a and b. So the thing is, can we find dy dx? Okay, so dy. Okay, because this is a curve. Because this is a curve. Okay, so here you can describe this as a functions. Here, can we describe as functions? Not say h of x. Locally. What means locally? At least piecewise, because you can describe this as a function up to this point. Then again, you can describe this as a function at this point. At least you need two functions to describe this in the shapes. That means local. Okay, and you would find some like a tangent of this curve at this point. So this tangent. So tangent, we know tangent is derivative. So what's the derivative? Okay, so this is if because the derivative is y, right? So dy dx. How to compute dy dx? If you're given the information of x in parametric form. Okay. So this is the idea. So dy dx is, if this is a parametric form, you can write down as dy dt over dx dt. All right, so pretend that dt cancel, so you're left with the dy over dx. Okay, so that's the idea. Okay. Let's do some example here. Find the equations for tangent line of a say of parametric curve. This is the easiest one. Again, cos t and sine t. This is upper semicircle. Right. At say 1/2 square root of 2, 1/2 square root of 2. Okay, so this is t equals, say this is t equals pi over 4. Okay, all right. Tangent, that means we need to find dy dx. Okay, of course you can find the y in terms of x. Okay, but we can do this directly from here. Okay, so dy over dx is dy over dt over dx over dt, dy over dt sine derivative cosine, and dx over dt cosine minus sine t. Okay, and you compute at t equals pi over 4. So you plug in pi over 4. Okay, so this is, there you go. And this is negative. Okay, so you have the equation for the line with this slope. This is slope. Right? Well, so you know that y minus here minus 1 times x minus there we go. So this is the equation for the line, for tangent line. And if you check, the graph looks like this one here, going this way. And square root of 2, well, 1/2 square root of 2 is okay. So the tangent is slope -1. Okay, so let's match up with our intuition that this slope must be 1. Okay, and one more thing. Suppose we have a parametric representations of a graph of functions, and you can try to find the area of by parametrically. So this is like f of x. It describes, say, xt is, say this one, with t from a to b. Okay. And from here, we like to find the area under the curve. Suppose this is negative, not negative. Curve. Okay. So suppose this is the graph looks like this. Okay. And you would like to find this area here. Okay. So the area here, we know this is the integral. So say this is between a and b, f of x dx. Okay. So, or we can write this down as f is y. This is dx. Okay. But we have this representation in parametric form. In parametric form, y is, well, whatever y there, y as a function of t now, okay? And then x, dx is x prime as a function of t dt. Remember, this is the differential. Okay. X is a function of t, so d sorry, I should write like this. D as a function of t. This is x prime times dt. So you have okay. So let's do this on a check with this a semicircle. So we know this has equations y equals from -1 to 1. Okay, and the area here is 1/2 of the area of the circle, radius 1. So it should be pi r square, r equals 1. So the whole circle is pi. So 1/2 is pi over 2. Okay, let's check with this integral. Okay. Getting this pi over 2 from this function is not easy, not an easy integral. Because if you do this one, you this is not an easy integral, as you might have seen from the method integrations. Okay, so but let's do this parametrically. So using parameter, we know that as usual, cosine t is sine t, but half circle, meaning that t goes from 0 to, say, pi. Okay, so the area is y dx. Okay, x equals -1 to 1, but that's the same as now in t, expressed in t. Y is sine t. Okay, and b of x cosine t. T from 0 to t to pi. Okay, so I intentionally write down using t equals something to remind you that the bound here must be in t, while here the bound is in x. Okay. All right, so let's compute this one. What you get here. So this is another sine, derivative of cosine, so another sine. All right, so that is integral of 0 to pi as negative sine square t dt. Okay, but then we know how to do this one because sine square is 1 minus 1 minus cosine square t, because this you have minus, then you put this back, cosine square t minus 1 dt. Okay, and write this cosine square as a 1/2 1 plus cosine 2t 1 dt. Okay, so it is integral of 0 to pi. So you have 1/2 minus 1. Well, put backward. All right, doesn't matter. Negative 1/2 and plus 1/2 cosine 2t dt. All right. So then you'd have negative t over 2 from here, and integral sine cosine is sine 1/2 plus 1/4 sine 2t. Plug in this. Sine 0 is 0, sine pi, so this is sine 2 pi is 0. So this gives you all 0. And remain this one here. Okay, so the only thing is, well, that's negative. Why that's negative? Is area negative? Why is this negative? That's because we are going from right to left. So that's negative. If we're going from this way, then you have a positive one. So going this way, the integral should be from here we get from pi to then you get this is positive pi over 2. Okay, so this negative is because we are going from here, going from right to left. Okay, but anyway, we somehow get this pi over 2 from this integral. Okay, questions? Okay, just one more example. Let's pick some problems. Oh, I'll show you just this one here. Example 6. Find the first two derivatives, dy dx, and second derivative, y all over x, for the function determined by this parametric. So 5 cosine pi, cosine t, y is 4 sine t. So this should be a, what do you call this? A semi-ellipse. And then evaluate. So compute dy dx. Dy dx is dy dt over dx dt. Well, we did as well. So the what is The second derivative. Second derivative is the derivative of the y prime, dx of the y prime. So here we have is dy prime over dt. So derivative of this and dx dt. So compute this one to get. And compute it at pi over 6. Plugged in pi over 6. You get this. Okay, here. Evaluate integral y dx, x y squared dx. But remember, this is x equals 1. This is x equals 3. So that's not t, but x. So somehow you get to replace the in terms of t, the bound in terms of t. So for example, this integral of y dx, integral of y dx is, let's see, this is still x. Now in terms of t, when x equals 1, t equals 1. So when x equals 3, t is 2. So now the bound for the integrals become from 1 to 2. This is y. This is the dx. Dx is just 2 dt. So let's do this one. Again, same thing here. Okay. Questions? Okay, let's do one more example of um, we haven't derived what's the area of an ellipse. Okay, so let's do area of an ellipse. The ellipse is this one here. Okay, so this is the ellipse. A, we know circle, but ellipse, we don't have the formula yet. So we will derive this. All right, so let's just compute the upper half one. Now compute the upper half. Now the area of an ellipse is just a twice of this. Okay, so the upper half ellipse in terms of parametric is, let's see, y equals, this is a cosine t, and y is b sine t. Okay, so you see that cosine is just x over a. So this is cosine, this is sine. And t from, let's see, 0 to pi. Again, this is going that direction. So you expect a negative number, and then the area is just the positive part. Okay, so let's compute this area there. So we compute this one. x equals from a to, wait, a to negative 8, or, sorry, I should write down as this one. A to x equals a, x. Okay, and in terms of t, so this y is b sine t, dx is uh, a derivative of this, so minus a sine t dt. Okay, if minus a, this is pi, this is from 0. Okay. Okay, so in order to make this one thing, so from 0 to pi, if you switch the bound, then you have negative, but then you have that negative will make this positive. Okay, so just AB sine square t dt. Okay. Okay. So you have AB sine square is just 1 minus over 2. It becomes 1 minus cosine 2t dt. Okay. So AB over 2, this is t, right? And minus 1/2 cosine, yeah, becomes sine, sine 2t to pi. Well, but with sine, this gives you 0. Okay, so then this is just pi. So at the end, this is what you get. AB pi. So the area of ellipse, the whole area. Ellipse, what's ellipse? Ellipse is this one. With minor and major axis is A and B. Length of it is AB times pi. Well, let's check this one. With A equals B equals 1, you get unit circle. That unit circle is area is where according to this it will be pi, and pi r squared. Right, so that's matched with the what we know what area of the circle. Okay, so this is the area of an ellipse. Just the length of the major minor axis. So sorry, radius, major radius, minor radius times p. Okay, questions? All right, if not, then we'll start with a factor, but we'll take a break for 5 to 10 minutes. All right. Stop share and stop record.